Okay, we are back. And so for this next segment, let's now go into the chemistry of electrophilic aromatic substitution. But now we are going to look at the mechanism. What if we had, actually, instead of an electron donating group, yeah, that's the better chemistry. But we're going to study what if our only option is that we have an electron withdrawing group that is bonded to our benzene ring. Okay, so this is not going to be very good chemistry. If we have our benzene ring with all those pi bonds only being partial double bonds, and then we add an electron withdrawing group that's pulling away even more electron density, then what is that going to do to our chemistry? That is going to really lower our chemistry. So when we have an electron withdrawing group that is bonded to our benzene ring, we say that this kind of structure is deactivated. So it is deactivated for electrophilic aromatic substitution. It is not going to do this chemistry very well. Okay, so this is going to be very poor chemistry. We are going to have a huge energy of activation in order to do chemistry at all. But let's talk about what if we go ahead, we add heat, we add a very strong electrophile. What chemistry can occur if we have an electron withdrawing group? Okay, I've done lots of doodling, so let's go ahead and take all that doodling away. Let's go ahead and bring back up a nice clean page. Actually, here we go, a nice clean page with electron withdrawing group highlighted. So what kind of chemistry will we do? Okay, so benzene ring, conjugated double bond system. I have my withdrawing group here. My withdrawing group pulling electron density away. I'm going to change to another color. So my question for you is, will this pi bond be very reactive? What do you think? I have a neighboring withdrawing group. It is pulling electron density away. Is that pi bond going to be able to at all act like a nucleophile and attack an electrophile? What do you think? Do you have an answer in your mind? I'll give you just a second to think. And the answer is absolutely not. So that pi bond is not going to be able to do chemistry. The pi bond that will do chemistry is going to be the pi bond that is more distant from the withdrawing group. And so that is going to be this pi bond right here. So this distant pi bond is going to be able to add to the new electrophile. So for this reason, we talk about electrophilic aromatic substitution with an electron withdrawing group as being deactivated. And we say that the withdrawing group is meta-directing. Any new group, if we do chemistry at all, the withdrawing group, so this withdrawing group is going to direct any new group to add to the meta position. And that is because it is only going to be the more distant pi bond that has any nucleophilic character. Okay, so my distant pi bond attacks the electrophile. Let me jump back over here to red again, draw everything out in red. And so then what is that intermediate going to look like? So I have my withdrawing group here. No chemistry at that pi bond, no chemistry at that pi bond. I add the new electrophile to the meta position. My other carbon gains the carbocation in character. Okay, let's go ahead and add resonance forms. So in all of the resonance forms, where would the positive charge be? So I would have a positive charge here, and I would have a positive charge here. Again, remembering I have a 1, a 3, and a 5 relationship between the position of the cation charges. What I want to highlight is that what is especially good about the metachemistry with the withdrawing group is that we never place the positive charge directly underneath this withdrawing group. That would be bad. That would be terrible if we had the positive charge underneath the withdrawing group. That carbon is already dipole positive, and to put a positive charge underneath that location would be terrible. Okay, so with electrophilic aromatic substitution with the withdrawing group, it is deactivated chemistry. Any chemistry happens at a meta position, and that chemistry happens for 2 reasons. The first is because we are reacting at the most dipole carbon that there is, the meta carbon. And then the second reason, we will never have a positive charge underneath the withdrawing group. So those are the 2 reasons why we conduct chemistry at the meta position with an electron withdrawing group. Okay, well, again, I kind of got scribbles all over again. I'm always getting distracted. So let's go ahead and draw this chemistry out one more time, nice and clean. Okay, so I have my pi bonds around my conjugated system. I have my withdrawing group. So I'm going to attack the electrophile with my most distant pi bond. I am going to add my new group to the meta position. And again, I've just told you the 2 reasons why we add the new group to the meta position. I get the carbocation here. Let's go ahead and draw in the other 2 positive charges for the resonance forms. And then just like before, I will have a base that is in solution. It is going to take a proton from the same carbon as the electrophile. Those protons move in to form the pi bond. And then for my final product, oh, I left off my withdrawing group here. I have my withdrawing group here. And then in the meta position, I have my new electrophile. And there it is. So then there's my mechanism with an electron withdrawing group. So the key things being that it is deactivated towards any chemistry, deactivated, and it is meta-directed for the 2 reasons that we have the most distant meta carbon as being the most dipole negative, and the second reason being that we never will have the carbocation underneath the electron withdrawing group. Okay, so then that kind of summarizes the mechanism with the electron withdrawing group. So let's look at some energy diagrams. So in going through both electron donating groups and withdrawing, if I have a donating group, what I want to highlight is doing chemistry at the orthopara, best kind of chemistry there is, because I'm doing chemistry at the most dipole negative carbons. Okay, and that's going to give us a majority of the product. So a majority of our product is going to come from adding the new electrophile at either of those 2 positions. I can do some chemistry at the meta position. It's higher in energy, but that both of those chemistries are much better than if I were to do chemistry with benzene itself. So benzene, unreactive, all partial double bond character. The best kind of chemistry is if I have an electron donating group and I put a new group orthopara. That is the best kind of chemistry. What is okay chemistry is if I add that new group to the meta position. And then what is not very good chemistry at all, so like not chemistry, would be doing chemistry with benzene. And then what did we just look at with the electron withdrawing group? Well, if we have an electron withdrawing group, so like here, what's pictured is nitro. Nitro, very much an electron withdrawing group. We're going to be able to barely do chemistry at all. So our benzene chemistry, which is not very good to begin with, is much better than meta chemistry. And then it is almost impossible to do ortho and para chemistry. So look at that energy diagram. It is terribly high. It is almost impossible to do electron withdrawing group chemistry at the ortho and para position. So a benzene will react faster than doing any chemistry at a meta position, which is better than ortho para if I have a withdrawing group that is bonded to my benzene ring. Okay, so to finish out this last section of just studying what does chemistry look like for electron donating or electron withdrawing, let's look at one more figure from your book. And so the figure from your book is highlighting that I have these activating ortho-para-directing. And here's like a good list of what are all the traditional activating ortho-para-directing groups. And then I have these deacting meta-directing groups. So all of these are electron withdrawing groups that we've been looking at for many weeks. But look who's here in the middle, the halogens. So the halogens are odd. Halogens are deactivating. They're deactivating. You are not going to do very good chemistry at all if you have a halogen bonded to the benzene ring. However, if you do chemistry, it will happen at the ortho-para direction. And let's look at why. Okay, so let's look at mechanism with halogens. So let's say I have this benzene ring. Here's my benzene ring. And I have a halogen that is bonded. Why will I go ahead and do chemistry at the ortho and para position? We're just going to look at ortho, and you can read in your book, look at other pictures about para. And so let's say I do chemistry with the ortho position. Is it going to be very good chemistry? No, I'm barely going to get any product. But notice when I do chemistry with that ortho pi bond, I will add the new electrophile to the ortho position. This becomes my carbocation. And I can stabilize that carbocation with a lone pair of the halogen. That is why we still have ortho-para directing with our halogens. Because even though the chemistry is deactivated, it is ortho-para directing because at least in the carbocation, there's a lone pair that can move in to help stabilize the carbocation. And so that is going to help just a little bit with the energy diagram with the halogen. Okay, so then to summarize, then I have my activating groups. Traditional activating groups are ortho-para directing. And then I have my halogens. So my halogens are actually deactivating, but they are also ortho-para directing. And then finally, we have our deactivators, our classic deactivators, and they always put any new group in the meta position. Okay, and so then that is how we summarize the chemistry of electrophilic aromatic substitution with activators and deactivators. So now you're going to take a quick quiz. It is all multiple choice to make sure that you understand the directing effects and the activating or deactivating effects. And then you're going to move on into actual chemical reactions. But first, you need to take a quick quiz. And so I will talk to you again after you have finished your quick quiz.